Hi, in this video we're going to look a little bit at the relationships between position, velocity, and acceleration, specifically as they are related to calculus. So there's a little summary here. This is also in your textbook in section 3.4 of your textbook. There's a little summary here. If we have a function that gives position of an object at a particular time, so that position might be something like height of an object that's being thrown into the air, or we could talk later about motion in different directions as well, but for right now most of the problems are about height of an object that's maybe being thrown into the air at a particular time t. So a couple of different vocabulary words here. Displacement, okay, that's just the change in position. So a few formulas to pay attention to here. Displacement is change in position. Average velocity is an average rate of change, so change in position with respect to time, delta s over delta t. Instantaneous rate of change, we already know that an instantaneous rate of change is going to be a derivative. So this is rate of change of position with respect to time. We call that velocity function. It's really an instantaneous velocity. Speed is related to velocity. Speed is something you can think about as you're driving or running or walking, but speed is just the absolute value of the velocity. Velocity could be negative. Speed won't be negative. And then acceleration, rate of change of velocity. So we can have an average acceleration. That would be just a change in velocity between two values over a time interval, or an instantaneous acceleration, so that's the derivative of the velocity function or the second derivative of the position function. Alright, so it's important that you know those formulas, how to find all those things. I guess I didn't highlight the speed ones, so we should highlight those as well. So you should know those formulas and how to find all those things. We're just going to look at an example where we're using those to answer some questions. Okay, so in this problem we have a function that gives the height in meters of an object fired into the air. So if you've had any physics, you might recognize this formula that comes from physics. So where these numbers are at in this equation comes from some physics principles, but for this problem you don't really have to know how to set up the height function. You're given this height function, but what you do want to understand is the relationships between that height function and velocity, acceleration, other things that it's asking about here. Alright, so the first thing that we're asked to do here is just to find the height of the object at t equals 0, 1, 2, and 3 seconds. So for that part, we're really just asked to plug in some t values into the position function just to get some output values here to help us as we answer some other questions here. So this is a good use for your calculator. You're just plugging these t values into your s of t function. So I'm going to have s of 0. I'm going to plug 0 into the s function, and I'll just get 5. That's meters, and t is in seconds. When I plug t equals 1 into my s function, I'll get s of 1, and we'll just evaluate that. Plug 1 into the s function, you should get 15.1 exactly meters. And then s of 2, plug that in, 2 into that position function, you should get 15.4 meters exactly. And then s of 3, just plugging 3 into the height function, and we'll get 5.9 meters. Okay, part B asks us to find some average velocities over different time intervals. And so remember that average velocity is a change in s over change in t. So we're going to look at a change in position over change in time. So our final position at t equals 1 is 15.1 minus our initial position at t equals 0, which was 5, and then subtracting the t values here, 1 minus 0. Okay, so we get 10.1, and that's a rate of change, so that would be in meters per second. It's an average velocity, how fast the object's going, and we've got a positive rate of change there over the first 1 second. Alright, and then over the next second, so between t equals 1 and t equals 2, we're going to look at that change in s over change in t. So I'm just doing my s of 2, which is 15.4 minus s of 1, which is 15.1 over 2 minus 1. Change in position over change in time. So for that we'll get 0.3 meters per second. And then over the third second, so from t equals 2 to t equals 3, our delta s over delta t in that time interval will be our final height, 5.9 at t equals 3, minus our height at t equals 2, 15.4, divided by 3 minus 2. So when we subtract that, be careful with the order on subtraction there. We'll get a negative 9.5 meters per second. So I've got a negative rate of change, which tells us that the object is getting lower. We actually already knew that from just thinking about those heights, but that's important to understand what that negative on that rate of change means. All right, so those are our answers right there for part B. The average velocity of the object over the first second, second, and third second. All right, part C and D asks us about instantaneous rates of change. So those are derivatives. So for part C, the instantaneous velocity, sometimes we write that as v of t, that is the derivative of our position function, so dsdt or s prime of t. And so when I find that derivative, I get 15 minus 9.8 t. And then I want to evaluate that at t equals 1, 2, and 3 as well. So we'll make a little chart here. Okay, so I'm just going to plug t equals 1, 2, and 3 into my velocity function, which is the derivative of the height function. So when I plug in t equals 1, I'll get v of 1. So 15 minus 9.8 times 1 will get 5.2. And that would be meters per second, a rate of change. That's an instantaneous rate of change, so that's how fast it's traveling at exactly t equals 1 second. And then t equals 2 seconds, when I plug in t equals 2 to my v function, I will get a negative rate of change, negative 4.6 meters per second. And then one more here, when I plug in t equals 3, I'll get v of 3 equals negative 14.4 meters per second. Okay, so those negative rates of change tell us something important here. The height has changed from getting bigger, a taller height, to getting smaller height. So somewhere in this time interval, sometime between t equals 1 second and t equals 2 seconds, the object switched from going up to going back down. So it changed direction. Somewhere between t equals 1 and t equals 2. That's what the change in sign on our velocity tells us. All right, for part D, it asks us about instantaneous speed, so I don't really have to do too much work with that. If I just remember that instantaneous speed is the absolute value of the velocity function. So I have my velocity values here, and so we can find the speed at each of those t values by just finding the absolute value of my answer. So 5.2 meters per second, 4.6 meters per second, and 14.4 meters per second. All right, so velocity has this positive or negative sign, which can help us indicate direction when the height or position is getting bigger or smaller. Speed strips that away, and it just focuses on how fast or slow an object is going. All right, so that was part D. All right, E asks us when the object changes direction from going up to going back down. So we're going to go back here and note that here we looked at this and we thought about what those velocities mean. I have a positive velocity at t equals 1, so that means my height is getting bigger. I have a negative velocity, a negative rate of change at t equals 2, so that means my height is getting smaller. So that means that somewhere in there it changed direction between t equals 1 and t equals 2. The other important idea there is that when the velocity is positive, the object is going up, And when the velocity is negative, the object is going down. So what I'm really looking for here for part E is I'm looking to find the t value when the velocity is 0, right? So that's really what part E is asking us to do. Understanding why that's what it's asking us to do is kind of understanding what it means when I have a positive velocity versus a negative velocity. All right, so to answer part E here, I'm just going to take my velocity function, 15 minus 9.8t, and I'm going to set that equal to 0 and solve for t. So I'll subtract 15 and divide by negative 9.8, and I'll get t equals 15 over 9.8, or if I want a decimal approximation for that, at about 1.531 seconds. Okay, part F asks us how high the object goes. So for part F, we're being asked to find a height here. Part F, we're being asked to find a height. That's a position at a particular time. So at the time when it changes from going up to going back down. So for part F, I'm really just going to use my answer from part E. I'm going to plug in that 15 over 9.8. That's the time when it changes from going up to going back down, and I just want to find out what its height is at that time. So I'm going to plug that 15 over 9.8 into the S function, into my original position function. You might notice that I used the exact value here and not the decimal approximation of 1.531. If you're only interested in approximate answers, then you can use the 1.531, but the more accurate you want your answer to be, the more you want to go back and use your exact answer and then round at the end. Alright, so I just plugged my 15 over 9.8 into my S function. I'm going to put that into my calculator, and I should get approximately 16.48 meters. So that's how high it is at its tallest height when it changes from going up to going back down. Alright, and then G and H ask us some things about what's happening when the object hits the ground. Okay, so important idea about that would be that when the object hits the ground, that would be when its height is 0. And we're asked for part G here to find the time, how long. And then for part H, how fast, so something about speed. So for part G, we just want to know the t when the height is 0. Okay, so for part G here, we're going to just set our height, which was s of t, to be 0, and then solve for t. So I'm just putting in 0 for the height for the output of that function, and then solving for t. Alright, so at this point, maybe you look at that for a minute, but hopefully pretty quickly you realize you've got a quadratic equation here. This is not one that factors, so quadratic formula is going to be the way to go. I might multiply through by -1 just to fix the signs on the right side, just so they're a little easier to work with, and put these terms in descending order of degree. So I just multiplied through by -1. As long as I do the same thing to both sides of the equation, that's alright. And then I'm going to use my quadratic formula here. So t equals negative b, so that'll be positive 15, plus or minus the square root of b squared, so negative 15 squared minus 4 times a is 4.9 times c is -5, all over 2a. Alright, so I'm just going to do my quadratic formula here. I'm going to just go ahead and get some approximate answers here. So when I do the 15 minus this whole square root, and the whole thing will be over 9.8, I'll get about -0.303. And then when I do the plus, I will get about 3.365. for my t values. Alright, so one of those doesn't really make sense in the context of the problem. In terms of a negative time, that would be before the object is even shot, so that wouldn't really make sense in the context of this problem. So t is approximately 3.365 seconds when the object hits the ground. All right, and then let's scroll back up and see what else it asked us. All right, so the last thing it asked us was how fast, so that's a speed of the object when it hits the ground. So a speed at that particular time, so we can just use our work from part G here to answer part H. We're asked to find speed. I'm going to use my velocity function, speed at that particular time, and I'm just going to use my decimal approximation here. So I'm just going to use the velocity function and evaluate that at 3.365 seconds. So I'm going to plug that into my velocity function. 15 minus 9.8 times 3.365. And I'm going to get an answer of about negative 17.97, and that would be meters per second. That's a negative rate of change. That's a velocity. It actually just asks us for speed, so the speed at that time would be the absolute value of that, so 17.97 meters per second. Okay, so the main thing to know from this section is the relationships between position, velocity, and acceleration, how you can find the derivative of position to find velocity, derivative of velocity to find acceleration, and then just how to answer a few questions related to those things.